This is chapter 1.4, functions. When we talk about functions, we're talking about something that you've seen as early as Algebra 1 and saw a lot as well in Algebra 2. But since functions are so important for calculus, we're going to spend time on it as well in this course. A function is a relation that assigns each element in one set of numbers, the domain, to exactly one element in another set of numbers, the range. All right, so think of it as a map. It's a relation is like a map where something in one set is being connected or matched with something in another set. That's basically all a function is. However, functions are written as equations, and that's how we're going to deal with them. A function is written as an equation whose independent variable, or input, is x, and whose dependent variable, or output, is f of x, or g of x, or h of x. You know there are many different letters that can be used to denote functions. Many letters of the alphabet, although the most common is f. Now, what does this mean, independent and dependent? All right, let's take a look at that in a chart. If we have this function, for example, f of x equals 4 divided by the quantity 3x squared. All right, that's our function. F of x equals 4 divided by the quantity 3x squared. Well, x is what I call my independent variable because x is what I plug in, and nothing changes the value I plug in. It's just, like in this case, x is 2. Well, 2 is 2. It's just a given. It's a given. It's independent. However, what's dependent is what comes out of the function, and that is what the value of f of x is. So if I plug the value 2 in to this function, well, what I get out of it is 1/3. All right, so that's why f of x, which we sometimes refer to as y, is my dependent variable, whereas x is my independent variable. We often call the independent variable the input because we're putting it into the function. And we often call the dependent variable the output because the function is putting that number out. All right, so this is just a quick review of terms. A lot of it you've seen already, but the review doesn't hurt. Here's another function, f of x equals 2 root x. We don't have to pick the value 9 for x. This is just a random value that we're picking to show you what effect the function has on what we plug in. But let's say we put 9 into this function, f of x equals 2 root x. Well, if I plug 9 in for x, and I see that root 9 is 3, 2 times 3 is 6, therefore f of x equals 6 when x equals 9. All right, notice how these right-hand values are dependent on these left-hand values because what's on the left goes into the function and what's on the right comes out of the function. All right, one more example. F of x equals x cubed plus 5x squared minus x. If I plug in -4, for example, if I plug that into this function for x, what I get out of it, the output, is 20. You can verify that by hand or on your calculator. But f of x equals 20. And so what did I plug in? I plugged in -4. What did I get out? What came out of the function? 20. All right, so again, quick review on inputs, outputs, independent variables, dependent variables. And in this chapter and in the rest of the book, we're going to always read f parentheses x as simply f of x, f of x. Now let's talk about domain and range. And we've touched on this briefly several times in the first semester. But now in the second semester, we're all going to become experts on domain and range. And domain and range is one of those concepts that a lot of students struggle with. So don't be surprised if it's difficult for you at first, because by the end of this semester, you should be pretty good at finding domain and range. All right, first let's review what domain and range is. The domain is the set of all possible values of x, or inputs for a function. That is, all the different numbers that I can put in to a function. That's my domain. There are some numbers that I can't put in. We'll get to that in a bit. But all the numbers that I can put in for x in a function, that constitutes my domain. The range is the set of all possible values of f of x, or outputs for a function. So, and the range depends on the input. So let's say that, I find my domain and I know what all the possible values of x are that can go into a function. Well, for that domain, there are there's a set of possible outputs that can come out of the function. All right, so the best way to learn this is with practice, and we're going to get a lot of practice on domain and range. Here are some examples, and you'll recognize these from the previous screen. In the previous screen, we used these specific functions with specific inputs and outputs. Now we're going to be more general, and that's going to illustrate the concept of domain and range. So the function f of x equals 3x squared plus 4. The domain is all real numbers, which I write as the interval from negative infinity to infinity. And the range is the interval from and including 4 up to positive infinity. Now, how do we get this? The way we get this is we have to ask ourselves some key questions. The first thing you have to find is the domain, and it's usually helpful to ask yourself this question when you're trying to find the domain. What numbers, if any, cannot be plugged into this function? Okay, I'm asking myself this question specifically here. F of x equals 3x squared plus 4, and I ask myself the question, what numbers, if any, cannot be plugged in? In other words, what numbers will give me an undefined result if I plug them in to this function? And the answer to that question is there are none, which means if no numbers do not work, then all numbers do. Okay, so it's usually best when you're finding domains to ask yourself the negative question first. When you find the answer to your negative question, that will give you the answer to the positive question, which is what numbers do work. Okay, so when you're finding domains, you ask yourself, what numbers, if any, don't work? And then once you find those, if any of them exist, then you will automatically have found what numbers do work, and therefore which numbers constitute your domain. Now, once you find your domain, well, then you ask yourself a positive question to get the range. And the positive question is this: well, given this domain, what can f of x be? All right. In other words, plugging in any numbers from this domain, what can I get for f of x? And that actually is simpler than you might imagine, because what you do is you try to find your endpoints. In other words, you try to find your low point of your interval and your high point of your interval. Okay, so just looking at this function now that I'm circling here, f of x equals 3x squared plus 4. Just looking at it, I know that whatever I plug in for x is going to yield a positive result because I'm squaring it. Okay, so then I have to ask myself, all right, well, how low can 3x squared go? How low can 3x squared go? Well, the smallest result is going to happen when I plug in 0 for x. anything bigger than 0 is going to give me a positive number for x squared. But 0 gives me 0 squared, which is 0, and that times 3 is 0. And therefore, the lowest that f of x can go is when I plug in 0, and that's how I get the lower limit of my range. Okay, so now I'm circling on the right-hand part of this chart the bracket 4. The bracket 4 means that 4 is the lowest value of the range. That's the smallest number I can get for f of x. Any other number I get for f of x is bigger than 4. All right, so I write 4 on the left-hand side. And then throwing in any other numbers from this large domain, I can see that whatever I get, it's going to be bigger than 4. And there's no limit to it. So therefore, my right-hand limit is positive infinity. So my range is bracket 4 comma infinity parentheses. Let's look at this function, f of x equals 2 root x. Again, we've seen this on the last screen, but now we're going to look at its domain and range. All right, well, how do I get this domain? I ask myself the negative question. All right, so looking now at this function, f of x equals 2 root x, I ask myself the negative question. What numbers, if any, cannot work if I plug them in for x? And the answer quickly becomes, well, the only numbers that won't work are negative. Therefore, the numbers that do work are not negative. And that means from 0 to infinity. Okay, so the domain then is what I get after I ask myself the negative question, what numbers can't work. And that in turn will show me what numbers do work. And those numbers are from 0 to positive infinity. Now 0, of course, notice that it's a bracket, not a parentheses. The parentheses means it doesn't include the endpoint, and the bracket means it does include the endpoint. And since I can find the square root of 0, which is 0, therefore the endpoint 0 is included in the domain. All right, now I found the domain. It's time to ask the positive question to get the range. Okay, the positive question is, okay, for this domain, what can f of x be? And so I want to look at, well, what's the lowest that f of x can be, and what's the highest that f of x can be? First, the lowest. Well, the lowest that f of x can be is going to happen when I plug in 0, because 2 root 0 is 0, and f of x is not going to ever be anything less than 0 because the root x can't be negative. Therefore, I've answered part of the question is that my lower limit, or the lowest that f of x can be, is bracket 0. The upper limit is going to be infinity because as I plug in larger and larger values of x, I'm going to get larger and larger values of root x, but there is no limit to how big root x can get. And therefore, my range is bracket 0 comma infinity parentheses. And a final example. And then, of course, in classwork, you'll be getting domains and ranges on your own. This is just to walk you through it a little bit. Let's look at this function, f of x equals x cubed plus 5x squared minus x. Well, the domain is all real numbers and the range is all real numbers. I can see that just from the chart, negative infinity, positive infinity, etc. But why is this true? Why is this true? Well, let's go step by step again. You want to get your domain, you have to ask yourself the negative question. What numbers, if any, cannot work for x if I plug them in? And looking at this polynomial, x cubed plus 5x squared minus x, I can see that every number will work if I plug it in for x. There are no limitations. Therefore, my domain is all real numbers. And now I ask myself the positive question. Given this domain of all real numbers, what is the lowest and highest that my f of x can be? And that is obviously negative infinity to positive infinity. How do you get that? Well, you can plug in theoretically small values, or large negative numbers. You can plug those in, because of course a large negative number is the same as a very small number. All right, you can plug those in, and you'll see that you get very large negative numbers. And if you plug in very large positive numbers, you'll see that the output is also very large positive numbers. Therefore, the range is also all real numbers. Now, what we've done is just looked at these algebraically, but what I'd like you to do now is graph these on your calculator. So graph each function separately on your calculator. That is, use a different set of axes for each graph. Observe the domain and range of each function. All right, so we're going to confirm now graphically what we just found algebraically. And you're going to see that your graph reflects these domains and ranges for each function, where the set of x values on each graph corresponds to the domain, and the set of y values corresponds to the range. For example, let's just go over this first one here. If I look at this first one, f of x equals 3x squared plus 4, negative infinity, infinity, and then 4 to infinity is my range. Well, if I graph this, I'm going to get a parabola that faces upward, and that's been shifted 4 units up. And on your graph, you're going to see that the y values go from 4 to infinity, and the x values go from negative infinity to infinity. So you can confirm this on your calculator. Let's do an example. A baseball is hit at a point 3 feet above ground around the batter's waist at a velocity of 100 feet per second and an angle of 45 degrees. The parabolic path of the ball is given by the function f of x equals negative 0.0032 x squared plus x plus 3, where x and f of x are measured in feet. So a little visual of this. Here we have a batter, and the batter is hitting the baseball. That's on the left. And then what I see on the right is I see the parabolic path of this baseball. Now, you can see algebraically, if you look at f of x, that you've got a negative coefficient of that x squared term. And what that means graphically is that, you know, the parabola is going to be facing downward. Okay, so this is actually how baseballs fly. They have a parabolic path. And if you look at the cursor right now, what I'm indicating is on this graph, you know, the y coordinates indicate height, and the x coordinates indicate distance from home plate. Well, you know, when the ball is hit, it's not right on the ground. It's a little bit above the ground, at the spot where the ball connects, you know, with the batter's bat. And then, of course, the ball goes upward on this parabolic path, and what constantly brings it downward is, of course, gravity, until finally the ball hits the ground, and that is the end of its flight. All right, so this is just a graphical model of a baseball hit. You don't need to worry about the velocity and the angle right now. You'll actually see that in physics. You're going to use the sine and cosine to get the horizontal and vertical components of the velocity. But for now, since we're just trying to learn functions, you can trust this model. And the model is negative 0.0032 x squared plus x plus 3. Those numbers change, of course, depending on the angle and the velocity. But for this particular angle and velocity, this parabolic path is described as such. Notice that the 3 here, the 3 in the polynomial, simply indicates at what height the ball is hit. And we can see that algebraically because when the ball is hit, the distance from home plate is 0, and if you plug in 0 for x, you end up with 3 for f of x, which is simply the height at which the ball was hit. All right, so this is what the example looks like, and here's the question. Will the baseball clear a 10-foot fence located 300 feet from home plate? All right, in other words, will this hit be a home run? Will the baseball clear a 10-foot fence located 300 feet from home plate? Now, I think you know enough to be able to do this on your own, using the fact that this is a function. F of x is the height, x is the distance from home plate. Put all that together and see if you can figure this out. So pause the video, do that on your own, and then resume when you have an answer. Well, when x equals 300, which is 300 feet from home plate, as the problem says, then f of x, the height, equals 15. That's what I get when I plug in 300 for x. And since 15, of course, is greater than 10, then this ball that was hit by the batter will clear the 10-foot fence, and it will be a home run. So the answer is yes. Here's the classwork. Please write these numbers down, and we'll see you in class.